Okay, I think we can begin with the part 2. So the problem that we want to solve here will be the ground state for the helium atom. Let me just erase. And what you will, so to make use of the variational principle, you know that the ground state for helium, whatever it will be, it has to be smaller than whatever expectation that we compute using some trial wave function. So we first have to guess what this trial wave function will be. And now if you look at this Hamiltonian for helium, it consists of the part there, that part there, and all these parts we actually know, right? So the problem was always this interaction part between the electrons. So if we didn't have that interaction part, the electron-electron part, VEE, this problem we could actually solve exactly. So let me use the white slide because it's going to be very long, messy computation. Hopefully do not get vectors wrong. White blackboard, right? Okay. So the goal is to try and get this minus 79 electron volt number for helium. So for helium, you will have, so you have the nucleus, which will have a charge, say it will have 2 protons, but then there will be some electron. The first electron will be at some position, the other one will be at another position, and then the distance between, so I'll call this position R1 vector, and the other one will be R2 vector. So this is the proton, the nucleus. Right. Now, classically, the energy of this system will just be given by the sum p squared over 2mi, the kinetic energies of all these particles, plus v of Ri, plus the interaction between the various R1, let's say R1, Ri, and Rj. So there will be some other part depending on the distances between the various particles. Let's say that this, then you have to sum through all these pairs of integers I and j. And quantum mechanically, once you do this canonical replacement, h bar over I d by dx, I have to erase everything. Let me use there. Then you get that the Hamiltonian will then be given by minus h bar squared over 2m for two particles. So there will be the delta 1 squared plus delta 2 squared, right, plus this term. So there are two of them. So this will give you, let's say, minus 2e squared over 4 pi epsilon 0 over r1 plus 1 over r2. Then there will be this messy interaction term between the two electrons. So this will be given by plus 1 over 4 pi epsilon 0, 1 over r1 plus minus, this is minus r2. Right. Now, if, as I keep saying, if this term was not there, right, this will be similar to what you had. I think I did this in the first lecture. Delta squared plus half omega squared, say x squared, plus y squared. Say you had in one dimension, this was dx squared plus d over dy squared, right? And I said that the unperturbed will just be the product. So this was an x0 tensor product with an y0. If this interaction term here, which is called VEE, if it wasn't there, what would be the wave function? And that is the wave function that we will use as our trial wave function. It's the same thing here. So it's just going to be, you can't label them by integers, but it's just going to be the product psi 100 at R1, psi 100 at R2. So this is what we are going to be using our trial function. We could have used anything. The point is that whatever thing that we get for the expectation value will be an upper bound. And physically, I think the first thing that you could try will just be the product of the two wave functions. So if you plug that into the remember that we want to find the expectation value. Let me just change color. Let's go and see. The first thing that we want to do is calculate the expected value of the tri using this tri. This is not the exact wave function for the helium atom, but if we do that, if we just use that one, same thing. So these two, right? This is erase, right? Everything. So the expectation value, right? Those minus h bar squared with delta squared, right? They will give you a term, and there are two of them, which they will basically give you the expectation value for the hydrogen atom. But unlike the atom, if you have a hydrogenic atom, say E, but instead of it having, maybe you have ZE, right? You can redo this type of problem, right? And what you get is that the energy is just Z squared multiplied by the 13.64 hydrogen. And this Z comes from the fact that when you were trying to solve your problem, instead of E at one point, you replace that E with the ZE. And this E1, if you remember, probably think it's E to the 4. So it's E squared squared. So for a hydrogenic atom with the charge there being plus ZE, you get to replace this by Z, ZE squared squared. What did I? I think it's Z E squared gets to be replaced by ZE squared, right? Because if you remember in the Bohr atom, you will have K, Q1, Q2. At one point, you wanted to calculate in the Bohr classical Bohr atom, and if this was the pure hydrogen atom, you ended up with K E squared over maybe R, right? Now for a hydrogenic atom, you have a ZE there. So if you replace Q1, Q2, at one point you ended up with K ZE for the nucleus multiplied by E, so divided by R. So this gave you K ZE squared. So in order for you to move from a pure hydrogen atom with one proton and one electron to these hydrogenic types, you have to make sure that you replace this ZE with a ZE squared. Now the energy E1 was going like E to the 4. So this means that this was E squared squared. You're replacing that by ZE squared. So there has to be Z squared. And for helium, the charge of the nucleus is 2 plus 2. So you get that 2 squared there. You do the same thing for remember this minus delta squared 1 with plus E over R, right? I'm saying that once you do that properly, you get that expectation, but there's another term which is minus delta 2 from the second electron, so that gives you that. So you end up with 2 times 4 E1. Then the remaining thing that will be left will be this VEE, right? And this is what we will be trying to get. So the VEE, if you write it down, so the first thing that you will have to do is that you have to choose your Cartesian system such that it passes through the nucleus and say one of the electrons. So this will be your R1. This is the second one. So this angle, you're just using spherical. So this is theta 2. And will be an angle there which is phi 2. And then the distance between these two, which is R1 minus R2. Right? And using high school maths, you know that the distance or the cosine rule will just be given by R1 squared plus R2 squared minus 2R1 R2 of cos theta. Right? So this is also what you're going to use. So what is the expectation value that we need to compute? So let's go. So the only thing left for us to calculate is VEE. So this will give you is R minus R1 minus R2. The hydrogenic wave functions, I think, might be a factor of 8. Let me write 8 over pi a cubed. It's just some constant, but the thing for us would be minus 4 R1 plus R2 over 4a. This is the Bohr radius. A is the Bohr radius, and then you are left with d3r1 d3r2. This is the integral that we have to do. So let's first do the integral over d3r2. So that integral, this r1 won't be contributing, so the only thing we have to look at is this one, that e to the minus r2 over 4a. So I'll call this integral I. It's going to be given by e to the minus 4 r2 over a over. Now this, you use the cosine rule, so this will just give you square root of r1 squared plus r2 squared minus 2r1 r2 cos theta 2. And then d3r is just the usual volume element, so it's going to have r2 squared sine theta 2 squared d theta d phi 2. Right. Now the full integral doesn't really depend on this d phi 2, so that will just give you a 2 pi. It's easy to do. Right. Then we will be left with the integral. So first have to do the integral 0 to pi of sine theta d theta 2 over square root r1 squared plus r2 squared minus 2r1 r2 cos theta 2. So what is the suggestion for this integral? If you do a u substitution, so you say u to be that, then du, this whole thing, so this integral then reduces into the square root of u, right? And then du will give you minus 2r1 r2 sine, I think it's plus sine theta 2, meaning that d theta 2 sine theta 2 will be given by 1 over r1 r2. Right? Is it true? Du. So everyone happy here? Or should I explain how I got that? And then this integral you can do, this just gives you 1 over 2 r1 r2 u to the minus half. I think it's plus half, right? it's u to the minus half, and maybe there is sort of a 2, and then you replace what the u will be. So this gives you r1 squared plus r2 squared minus 2 r1 r2 cos theta 2 from 0 to pi over r1 r2. Right. So just when you get the pi, that gives you r1 squared plus so you just plug in the limits, then you get that integral is given by 1 over r1 r2 of square root r1 squared plus r2 squared plus 2 r1 r2 minus square root r1 squared plus r2 squared minus, you're basically substituting cos pi and also cos 0. One is minus 1, the other is 1. So 2 r1 r2, right? And this is just the square. So you get 1 over r1 r2 of r1 plus r2 squared. Take the square root, you get r1 plus r2. But the second one you have to be careful because it will depend on whether r1 is smaller than r2 or r2 is the one which is smaller than r1. So you have to take the mod because this is this thing there is just r1 minus r2 squared, and the square root is the mod. So you have to take the mod, r1 minus r2, and then you split it into these two cases. So let's say that r1 was the greater one. So in that case, you get 1 over r1 r2 r1 plus r2 minus r1 minus r2. So the r1 cancels with that r1, so you're left with 2 r2 over r1 r2. So this gives you 2 over r1. Similarly, the other case, which was r1 smaller than r2, you can do the same thing, right? The only difference, let me use a different color. The only difference is that now that mod there gets to be replaced by r2 minus r1, right? It's a minus, and now the terms that will be cancelling will be that r2, right? Will cancel with that one, so you're left with 2 over r2. So that means that that integral is either into 2, so it's either 2 over r1 or 2 over r2. This is the result for the integral over d theta 2. So then we are left with an integral over r1, not an integral over r2. So what then we do, we split our integral so that we have, remember that we'll have integral 0 to infinity of dr2. This, we take this to be 0 to r1 plus 0 to r, or let's say that r1 to infinity, right? And then we use the condition. So in this, remember that we're integrating over dr2. So this set of limits means that r1 is the one which is, or r2 smaller than r1, right? So then you use the condition that I gave, plug everything into there, so you end with equals to 1 over r1 integral 0 r1 a minus 4 r over a r2 squared dr2 plus 1 over, okay, I think they will cancel for the other, so you get r1 to infinity of e minus 4 r2 over a r2 dr2. Right? I'm saying that for this one, once you use that condition that it's either 2 over r1 or it's 2 over r2. So you are left with this type with only integrals over r. I think this is r2. So you are only left with integrals of the form d, let's say dx xn e to the minus beta x from a to b. Right? So how then, and because you need these types of integrals, so I'm calling this n a comma b. You need these types of integrals in order for you to express these. So how do you get those integrals? So if I'm happy that I0, say a and b, this is integral from a to b dx e minus beta x. What is this integral? It's just going to give you 1 over e 1 minus e to the minus beta x, right? And then you evaluate a to b, so you get e to the minus beta b minus e to the minus beta a over minus beta. And then to get, say, if you wanted an x1 there, we've done this trick last year, so you just differentiate with respect to beta. So if you differentiate, if you wanted to get the integral with an xn there, you differentiate d over d beta and times minus 1 of what I called I0 AB. And you can check that the integrals that you are looking for are, say, the first two. So you get I2 of 0 and R. Just make use of this result and plug it there. So will give you 1 over beta cubed 2 minus 2 plus R1 beta plus R1 squared beta squared plus E minus beta R. It's this thing that some of these integrals that you have to do are really messy, but this is the result that you get. Similarly for I1, the other one, it was going from R to infinity, you get 1 over beta squared 1 plus beta R1 minus beta R1. I think this is all. So these are the integrals over R that we need, and I think beta in that case it was e to the minus 4 over a. So this is what beta would be. So let's go back to the slides. I think I've explained everything. But we are still not done. It's one of those long so this is the term that we actually wanted to compute. So we started by trying to do the integral over dr2. Right. Then we made use of the cosine rule. Then we changed parameters, so we let u to be the thing that was inside the square root. So we let this to be our u. Then this transformed our integral into something like integral du square root of u, which evaluated into just square root of u between 0 and pi. Once we did once we substituted these two values, we ended up with this one. This one we know it's just r1 plus r2 squared. So once we take the square root, we don't have to take the mod because it's always positive. The problem was this one. This is r1 minus r2, but we don't know whether r2 is smaller or r1 is the one which is smaller. So depending on which of these two cases, we either end up with 2 over r1 or 2 over r2. Then you split this. So this condition means that 0 is smaller than r2, smaller than r1. So for this part of the integral, let's call this I theta. Is I theta, the final by r2 by 2 over r1. So you had something like 2 over r1, so which is just a constant, so you took it out. Right? So you're left with r2 squared. Then the other one will be this case here. So between r1 and r theta, you have to plug in 2 over r1. So you get 2 over r2, but there's an r2 squared coming from dv. Right? So that cancels, and you're only left with this r2 squared and r2. And these integrals is what I told you how to compute, because if you are calling beta to be 4r over a, these integrals are of the form xn e to the minus beta x between a and b. And I've shown you how to compute those types of integrals, plug them there for different. You have to calculate I2 and I1, which I showed you on the whiteboard. Once you do that, this is the result that you get. But we are still not yet done, because you see, remember that we have basically you are trying to do a 6-dimensional integral. So there are 6 integrals that you have to do. So far we have only managed to do the 3 integrals, but you still have to do the other 3 volume integrals, which are integrals over dr3r1 of what we obtained. So if you look at the previous slide, with 1 plus 2r1 over a e to the minus 4 r1 over a, but the wave function for psi r1 also is 4r1 over a. So you still have to multiply that by minus 4r1 over a. And this is just the usual volume element. Right? Now again, this entire integral doesn't really depend on phi. So, and I think also on d phi. Right? So this means that the integral over sine theta, right, sine theta d phi, this integral you can do, and this just gives you the full volume omega for the angle for the sphere, which is 4 pi. Right. So the only integrals that we then are left with are e to the minus 4, these types, and you use the same formula that I gave you, but now you're going from 0 to infinity. And I think these ones you should be able to do, right? So if you look at I0, it's just integral dr e minus beta r r to the 0. So this just gives you, and I think it's 0 to infinity. This just gives you minus 1 over beta. Then I1, then to get I1, you differentiate I0 with respect to beta. When you differentiate the exponential, that brings a factor of r at the bottom. So I1 will just be differentiated. You get minus, I think, 1 over beta squared, and then I2. Right, so I2 will be integral of R2 e to the minus beta R, 0 infinity. This, once you differentiate that, I get minus 2 over beta 3. Right? So integral R dr, so let's say that there's an R. So just remember that 0 is beta to the 1, 1 is 2, and 2 gives you 3. So let's clear everything and write what the expressions that we get. So the integral over R, this is like this will give you 1 over beta squared. Similarly for this one, this gives you 1 over beta squared. This other one gives you 2 over a. 2 gives, there was a 2 there, over beta to the cubed. Then yeah, this beta is different from the other ones. Right? Beta is this 4 over a there. Beta here is 8 over a. So once you plug everything there, so I'm saying that the integral r to the minus 4r over a, that integral will just give you a squared over 4 squared minus this one will give you 1 over beta squared, but a different beta, so it's just a squared over 8 squared plus 2 times 2 over a of a cubed over what would it be, over 8 cubed. Right? And if you plug all these numbers, you get a squared, set out the effect of 1 over a squared, you get 1 over 4 squared minus 1 over 8 squared minus 2 times 2 over 8 cubed. And this gives you 5 over 128. Just check that. And then this a cubed. Right? So this is the end result of all these long computations. That integral that we wanted to do is given by 5 over 128 a squared. Then you plug it into VEE. Can remember how VEE is proportional to delta 5 over, so and then you know what is the Bohr radius, but at the end you get this, which is 5 over 2 once you rewritten everything in terms of E1. So if you remember, in terms of the Bohr radius, I think there's a half root of half, and it's 1 over 4 pi epsilon 0 times the Bohr radius. So this whole thing up to a factor of 2 is just E1, and E1 is 13.6, so you get this 34. So although it took me like very long time, the point is that at the end you get this 5 over 128, and VEE is just this 34 11 volts. So the full thing will be that there was that 8 multiplied by E1, which will give you that minus 109 34 electron volts. This gives you minus 75, but which is very impressive, because if you remember, the final answer that we wanted was the minus 79. So these variational methods to give answers that are not only simple but actually very close to the answer. And the trial wave function that we did was very simple. We just took the product of the two, so R1 and R2. But for a more realistic one, so if you remember, in one of the problems that I did, you'll end up with the trial wave function. You can choose it to depend, maybe in one of the problems I chose it to depend on two parameters, alpha and beta, and then you try to minimize with respect to alpha, with respect to beta. if you look in the first lecture, I tried to like that. It's just that there I said that, well, I had already had the condition for beta in terms of alpha, so I just plugged it there. But we have to introduce another parameter, and physically what this parameter means is that, let's say that you're looking at the, so you have some charge, and then you have some other electron which is far away, but there will be some electron cloud. So this charge, this electron there doesn't really see the full, doesn't really feel the full charge. So it feels something charged. I think that for helium, it feels a charge of 2e. It feels a reduced charge. So that reduced charge, I'm going to replace it, call it ZE, and introduce this into the wave function. I did this so the excitation for hydrogenic atom with a ZE there is just given by Z squared E1. You can check this. And there are two such contributions, because one contribution coming from the Laplacian for delta for R1, the other one coming, so there are two of them. But you are going to end up getting an expression that is being written, okay, in terms of these Z's. So Z again is a parameter. So the first thing that you have to do is that your original hydrogen Hamiltonian for the helium atom, although in this thing we can play around with various parameters, the Hamiltonian doesn't really change. So if you looked at what I did, so these terms were not there initially. So you only, if you remember what I wrote, you have pi squared over 2m plus v of r I plus this term v, depending on the difference. But this term, I think it was a 2 there and a 2. What? But we want to add information to write Hamiltonian in terms of another Hamiltonian, which is measuring how much charge actually feeling out of the charge. So in order to do that, if you look at the first term, which is, so we are not going to touch those parts, the kinetic part. We are only going to, if you look at 2, so I'm going to write that 2 as 2 plus z minus z. Right? So I've not really done anything, but the z minus 2, I write it there. It's the same term, right? I've not done anything. I'm rewriting the 2 as 2 plus z minus z. And then z minus 2 stands there. And then this part z there, it's the thing that will be sitting there. Right? And I do the same thing for R2. So I just write 2 as 2 plus z minus z, and then I separate. So I end up with a Hamiltonian that, depending on this z parameter, right? Clear, right? Then I use my trial wave function, which I can choose to be anything, and it could depend on any parameter. So I've said that this will be going like minus z over, let's say, 2 there, a0, the normal, and it has to be normalized. So initially I would have turned this to be a, but once I try to normalize, I get something that will be depending on z. I think it's depending on z cubed, and e to the minus zr over a 0. Then I take this trial wave function and I compute the expectation value using that thing. So these ones will not change. So you get these, you get what you got previously. Let's say 2 squared E1. I explained you get this Z squared from this kinetic part, and which is, well, it's this whole thing here, right? The expectation value of that will give you this, and then you're left with z minus 2, right? It's a parameter, but depending, the coordinates. So this constant, so you're left with 2z minus 2. Then you have to find what is the expectation value of 1 over r. It is the same as the expectation value of 1 over r2 because they are dummy variables. The r side 1 over r, whether you call this thing r1 or r2 doesn't matter. So in the end, I'll just call it r1. So, and then the other expectation value, this expectation value we have computed. And similarly, this expectation value I computed using the Feynman theorem previously. So if you remember, for the fine structure, we had to compute things like r 1 over r squared expectation, and also, but my point is that we already know like what the answer is. So if you plug everything into the expectation value with that trial in terms of these z's, this is what you get. So this again is just some energy depending on z, but and it will be an upper bound on the ground state. So to get to the ground state with as e, so we differentiate that with respect to dz. So for the z 27 over 4 squared, then take that z back there. So no, so whatever z we get, 27 over 4 squared, we plug it into that. Is this correct? You get 1.61. This is going like z squared. Just take this value and plug it into that previous expression in the 1.69. Z is 1.69. You put it here. And you get this, which is, once you plug in the numerical values, you get 77.5 minus 77.5 electron volt, which is not that bad because we are looking at something like 79. So this method is simple to implement. You just calculate h of alpha and then try to minimize that and look at what you're getting. You're getting things that are very close to the experimentally correct thing. Then I just said using the ground state for hydrogen, try to calculate the ionization energy. So the ionization energy is the electron we need to add, to remove one electron from helium. Right. So let's say you start a nucleus, meaning that you're taking one of them to infinity. So once this electron is removed, what is the energy of this one? The energy of this one you calculated is that 2 z squared. What? Maybe it's just the z squared E1. So for this one there is no shielding, so that is just 2. So you end up with 2 squared minus that one. So it's just E final. Once you've removed or moved this electron to infinity, subtracted the original ion the system, which was the minus 79 electron volt. So this gives you 24.6, but I've not checked what the experimental value is. So the next system that we will be looking at will be the hydrogen molecule. So yeah, I think I should leave it here. So I think in the next lecture I will go through because again it's going to take too long. So I will go through the hydrogen molecule example in the next example. or next lecture, and I will post in the slides. I think a day before. So the next lecture will be on Tuesday. I'll try to post them on Monday so that you can go through them. I'll post the lecture slides for what we did today. Okay. And for those who came in late, the date is on Wednesday. So if you have any problems or you cannot solve some integrals, you should then email me. I should be able to give you what those results are. For the diagonalization part, which is let's just go back. If I say that you should use first diagonalization theory, and this by a matrix. What I mean is that you form the eigenvectors, so you get A1, A2, A3. Remember that the first order correction is given by something like that. It's an inner product. It's just that in this case you're not looking at L2 AB, this Hilbert space, which means that the inner product was given by dx psi. These are just matrices, so this type of notation means that you have to then form this other, and then A1, A2, A3. Right. So, for example, for the, I think it's C, this is what you have to do. You have to find the eigenvectors, take the transpose, find this vector, and then try to find this inner product. This will give you the corrections for those things that have matrices. And I think even for 3C, because for 3C you can write that H as that the lambda, the one with the lambda, and then Lx minus Ly squared. You can write this as a matrix. You can diagonalize that matrix, and you can do something similar if you want to compare with what the results that you get for first question theory. Right. Are there any questions? Because I am thinking of stopping the recording. Okay.